Okay, so now let's have an exercise with allelic and genotypic frequencies, so-called Hardy-Weinberg principle. This is a famous problem. So consider a gene with two alleles, large A and small a. If the allele for brown hair is dominant over the allele for blonde hair, which is a small a, how does the blonde trait remain in the population? So let's assume a frequency of allele large A as a P in the population. And again, the frequency of allele of small a, which is a blonde hair, is Q. Then assuming if there's only these two alleles in a population, then the probability of P plus Q, because all the alleles are large A and small a, it's gonna be 1. Okay, so at some time point, assume the frequency of allele A and frequency of allele small a in a population is given as, let's say, P equals 0.8. So 80%, and Q, the frequency of the allele is Q is 0.2. Then what happens for the second generation? So the second generation, the gene, let's start to think and calculate this. So the second generation with a male and female, assuming a random mating, so male and female, then the allele for large A, the probability is 0.8. Allele for small a, probability of 0.2. And likewise, female is the same. Allele for large A is 0.8. Allele for small a is probability 0.2. So what happens? When this random mating, the progeny of F2 generation will be capital AA, and the probability will be multiplication, so that's P squared. What about this large A, small a? The probability is PQ, and this small a, large a, probability will be QP, and small a, and that probability will be Q squared. So genotype for the second generation and the probability of genotype of, let's say, capital AA will be P squared, which is 0.8 squared or 0.64. And what about the heterozygous one, large A, small a, will be, there's a 1 PQ, 1 QP, so that's 2 PQ, and that will be 2 times 0.8 times 0.2 will be 0.32. And what about the probability of genotype of small a will be Q squared, which is 0.2 squared or 0.04. And you can see this probability, or the sum would be 1. Then now, to go back to the question of the allelic frequency. So let's discuss about what's the frequency of the alleles in the offspring. So the frequency of alleles in the offspring generation. And assume with n individuals. So there's n individual in the second generation. Then let's calculate frequency of large A will be total number of alleles and the number of alleles with large A. So how do we calculate that? So with n individuals, alleles will be 2 for per individual. So total number of allele will be 2n. And this allele A, let's say allele A will be found here, allele A is found here and here. So that means, so first this one, homozygous capital A will have 2 of alleles. So 2 times, and the probability is p squared, so p squared, and the individual is n, right? And the other is this has 1 allele and this has 1 allele. So each has PQ. So that is probability PQ, but there are 2 of these groups and times the individual number is n. So that's what we can see. And let's calculate is we can cancel out this NN and 2. That is P squared plus PQ, or P plus Q, which is 1. And so the result would be P. Likewise, let's calculate allelic frequency of small a is, again, total number of alleles of small a, total number with 2n. Now we can see small a, so there's AA, so this is 2 times AA and the probability to Q squared, and total, this is probability, so we need to multiply the number of individuals to have the actual number of alleles, so times n. Plus, likewise, there's small a here, so there's 2 of this and with the probabilities PQ, so that is probability of PQ, and there are 2 of this, and then individual n. So likewise, if we calculate this, this will exactly come out as a Q. So what does this mean to us? So it turns out that the frequency of alleles, stay constant because it remains the same, P and Q, from generation, the top generation to the next generation. So this is a very interesting thing, that the allele frequency remains the same from top generation, parent generation to the next offspring generation. And here we have to note that there's an assumption. We are assuming that there are random mating. So there's no specific force or no selective pressure involved. Okay, that's when this happens true. But there could be exceptions for this. So for example, so what if there's an external factor that inheritance pattern, this may change. So if other factors such as factors then may affect this, would be, for example, gene mutation, such as, let's say, large A becomes small a, or assuming this population has influx or outflux from other societies. So that means gene flow. into the population. Or what if there's eugenics involved and people try to, let's say, get married to a certain specific trait? That could be a problem. So for in this aspect, so that's like selective breeding among subpopulation. Or like natural selection. So what if maybe some specific trait is like overpowered and maybe survive better than the other, then it could change. Okay, this is what I want to share, and thank you for your attention.